In levels of ecological organization, single organisms are usually the lowest level we deal with. The level right above organisms is the subject of this video. This is video 4.2 on populations. We've got a lot of ground to cover. These 7 goals. Pause the video to take a closer look, then buckle your seatbelt because we've got a lot to do. We can't really start a video about populations without a solid definition of the word populations. Populations are groups of organisms of the same species, but it's really more than that. More accurately, populations are groups of organisms of the same species, living in the same place at the same time, and using the same resources. Organisms in the same population interact with one another as well as interbreed. The focus of this video is going to be demographics. Demographics are just statistical data about populations. We'll look at some examples of statistical data presentations and then talk about what you can infer about populations based on the patterns in the data. The 3 main types of demographics we'll see are life tables, survivorship curves, and population growth curves. For each of these 3 types of demographics, I want you to focus on what information is given and what information can be inferred based on the information that's given. Let's start with a life table. Here's an example of a life table for Belding's ground squirrels. Now, these cute little guys down here. At a glance, you can see that the table splits males and females and follows males and females through a time period of 10 years. And here's what a life table shows us. A life table follows a cohort of organisms throughout their whole life. A cohort is a group of organisms that are born around the same time, and so like a good example of a cohort is high school students. High school seniors all started kindergarten together and then went through first grade, second grade, third grade, all of those stages together through school as a cohort, a group with a common pathway. Juniors would be a separate cohort, sophomores would be a separate cohort, and freshmen and so on. So hopefully you get the idea. So now we have a cohort of Belding's ground squirrels that were all born around the same time, and scientists follow them throughout their whole life. So what's given in a life table is survival data about a cohort. You can see that this table gives the number alive at the start of the year, then the proportion of the original population that's still alive. Next is how many organisms die in a given year, which is then used to calculate the death rate of that year. And last is life expectancy. So how much longer will these survivors expect to live after that year? This given survival information can be used by ecologists to make inferences. 2 of the most common inferences include sources of mortality and reproductive strategies. If we look at this example with ground squirrels, we can see that the death rate of the females stays pretty constant throughout the 10 years. Males, on the other hand, have a higher death rate than females, especially in years 3 and 4. What can I do with this information? Well, here's an example. Belding's ground squirrels exhibit alarm call behavior. When a predator is nearby, one squirrel will call out to the group to alert the squirrels to the predator's presence. Unfortunately, that squirrel that's doing the calling draws the predator's attention. So, based on this data, I'd guess that males act as the alarm callers more frequently than females, and that might be the cause of the higher death rate. Is that true? Well, I don't know, but it serves as a hypothesis to focus my next steps if I was interested in studying that. Our next representation of demographics is a survivorship curve. A survivorship curve is just a graph of a life table. Let's see. So what's given on a survivorship curve? Well, here's a survivorship curve, and you can see that it's a graph of the proportion of a cohort still alive at each age. Focusing on the axes, you can see that the y-axis is survival per 1,000 individuals in a cohort, But the scaling is different. This y-axis has a log scale. See how the intervals are evenly spaced, but it goes 1,000, 100, 10, and 1? That's what a log scale is. Now, what's given on the y-axis is time. The time on the y-axis can differ from one survivorship curve to the next, but what's true of all survivorship curves is that the amount of time should be equal to one lifetime. To relate survivorship curves to life tables, what's being graphed is this column, the proportion alive at the start of the year. Now, the survivorship curve isn't separating out males and females, it's just batching this data together. Survivorship curves can follow distinct patterns like those in this example. The green curve is called a type 1 survivorship curve. You can see that the organisms with type 1 survivorship have relatively low death rate, most of them staying alive until very late in life. In contrast, the red curve is a type 3 survivorship curve. Organisms with type 3 survivorship show most of the population dying very, very early, with very few making it to reproductive maturity and adulthood. Type 2 is kind of in the middle. Organisms with type 2 survivorship are characterized by a relatively constant death rate throughout their life. One way I personally like to think about it is, when are there only 10% of the organisms alive? In other words, when has 90% of the cohort died? 10% survival of a starting cohort of 1,000 is 100 survivors. Let's draw a line there. Okay, so now draw a line down where this line intersects with each survivorship curve. Here we go. So type 1 survivorship means that 10% of the cohort remains at about 90% through the lifespan. For type 2, 10% are still alive, or 90% have died about 1/3 of the way through the lifespan. And in type 3, there are only 10% of survivors, only about 3% through their lifespan. So 90% of these organisms die within the first 3% of their lifespan. So this is the data that's given on a survivorship curve, and scientists can actually infer what's known as life history. Life history includes trends in reproduction, growth, development, and survival. Let's dive a little deeper into that. To talk about reproduction and life history, we have to use the word fecundity. Fecundity means the capacity for reproduction. In other words, how many offspring can an organism make in its whole life? Organisms that have high fecundity tend to have certain characteristics. High fecundity usually means a young age at first reproduction, high number of offspring in each reproductive cycle, a high frequency of reproductive cycles where an organism can reproduce again right after having babies, and a relatively old age of last reproduction. All of these elements add up to making a lot of offspring in one lifetime. Moreover, organisms with high fecundity tend to invest very little in each offspring. What this means is that each offspring tends to be pretty small, and most of the time, the parent organism doesn't invest any paternal care. Overall, these strategies are designed to save energy with the goal of making more offspring faster. Now remember, fitness is the ability to survive and reproduce. So does maximum fecundity mean maximum fitness? I'll let you be the judge. Okay, let's tie back to our survivorship curves. Type 1 survivorship species tend to be K-selected species, and type 3 survivorship species tend to be R-selected species. K-selected and R-selected refer to the life histories, which have a lot to do with reproductive strategies. So let's check it out. Type 1 species have the K-selected life history. These species maximize the survival of each offspring. To this end, type 1 K-selected species tend to start reproducing relatively late in life, have just a few large offspring at a time and invest a lot of time and energy in parental care. Examples of type 1 K-selected species include primates and coconut trees. In contrast, type 3 species have an R-selected life history. These species maximize fecundity, having the highest number of offspring possible. Type 3 R-selected species tend to start reproducing relatively early in life and have a whole bunch of small offspring. Moreover, there tends to be very little energy and time invested in parenting, and examples of type 3 R-selected species include insects and plants that make a whole bunch of seeds at one time. K-selected and R-selected species also have characteristic population growth curves. As seen here, K-selected species tend to have relatively steady populations that stay pretty constant around the carrying capacity. On the other hand, R-selected species have population growth curves that can fluctuate wildly in what's called a boom and bust curve. And that leads us nicely into our last demographic statistic, population growth curves. Now, population sizes can increase and decrease based on some basic factors. Population sizes can increase when more organisms are born or when organisms immigrate into a population from another population. Population sizes can decrease when organisms die or when organisms emigrate away from the population. Check out this poor bird right here. Watch out, little dude. Here's what a population growth curve looks like. It's a graph where the y-axis is population size. Now, this time, population size is in a linear scale, not a log scale. Population size is often abbreviated with a capital N. Then, on the y-axis is time. Unlike a survivorship curve, which had a time scale of 1 lifetime, population growth curves have a time scale of many generations. So, what's given to us is information about how the number of individuals in a population changes over a time frame of many generations. When looking at population growth curves, there are two patterns that will jump out: exponential growth and logistic growth. Exponential growth is sometimes called a J-curve, because it looks like a J. What you can infer if you see exponential growth is that this organism is experiencing pretty perfect conditions. And what I mean by that is that food is super abundant, living space is super abundant, there are no predators and no diseases stopping the growth of this population. In exponential growth, there is an initial lag phase with slow growth because there are only a few individuals to start off with, but when reproduction gets going, look out. The population size takes off in a hurry. In nature, exponential growth is actually pretty rare. Situations where exponential growth is seen is when a species is newly introduced to an area or when a species is rebounding from an environmental catastrophe that caused a population bottleneck. If you're looking to make connections, both of these can be related back to evolution with genetic drift and the founder effect and bottleneck effect. So here are two examples. Whooping cranes were nearly extinct in the 1930s due to habitat loss and overhunting. Likewise, African elephants were nearly extinct in the early 1900s because of hunting in the ivory trade. Hunting and habitat loss created population bottlenecks for each species. But once measures were put in place to protect their populations, both of these species experienced exponential growth. The other type of population growth curve pattern is logistic growth, also known as an S-curve, because it looks like an S. Logistic growth has the same lag phase and rapid growth phase as exponential growth, but in logistic growth, eventually the population growth slows and then reaches a plateau. The plateau of logistic growth is called the carrying capacity, abbreviated by the letter capital K. When scientists see a logistic growth pattern, they can infer then the population is experiencing a limiting resource. The limiting resource creates competition that causes the population growth to slow and eventually flatten out at the carrying capacity. The idea of carrying capacity is worthy of a closer look. The definition for carrying capacity would be the maximum population an environment can support with no degradation of the habitat. So you can see on this population growth curve of these fur seals that the carrying capacity is somewhere about 10,000 male fur seals. So populations that display logistic growth curves or the carrying capacity are under the influence of limiting factors. We call these types of limiting factors density-dependent limiting factors. Density-dependent limiting factors are factors where the effect on a population intensifies in larger populations. This includes factors like food, space, and water that organisms would have to compete for. The more individuals there are, the more competition there is. Other density-dependent factors include predators and parasites and pathogens or diseases. It's very easy for predators to kill prey when the prey is more densely populated. Likewise, organisms in dense populations are more likely to spread parasites and disease to one another because of the overcrowding. Population size can also be affected by density-independent factors. These factors are ones that affect large and small populations to the same extent. Density-independent factors tend to be abiotic or non-living things like seasonal weather changes, natural disasters, and human interactions like habitat loss. Imagine a mosquito population. Once the weather changes, regardless of a mosquito population being large or small, the cold weather is going to kill them off no matter what. You can tell what type of factors are affecting a population based on the shape of the population growth curve. Remember, a J-curve shows exponential growth, a population where there are no factors limiting the growth of that population. A classic S-curve shows logistic growth, where the population is affected by density-dependent factors. A population affected by density-independent factors tends to look like it's a J-curve, but then that population experiences rapid decreases whenever a density-independent factor kicks in. Oh man, that was a lot. So let's recap. This video is about populations, groups of organisms of the same species living in the same place and using the same resources. Populations can be characterized by demographics, which are statistics that, based on their patterns, can be used to predict certain things about the population. Life tables and survivorship curves show the same demographic in two different ways. Both give you the statistics of a proportion of a cohort surviving throughout one lifetime. The patterns you can see are type 1, type 2, or type 3 survivorship. Based on these patterns, you can infer life history, where type 1 organisms tend to be K-selected species, and type 3 survivorship organisms tend to have R-selected life histories. Finally, population growth curves can give the information of a population size over several generations. Based on the shape of the population growth curve, you can infer what types of limiting factors the population is experiencing, if they're experiencing any at all.